Hi, welcome to our first lesson for Chapter 2, Transformations of Functions. So in this chapter, we're going to learn how to determine if two algebraic expressions are equivalent. We're going to learn how to work with rational expressions, and um, we're going to learn about all the different transformations that can be applied to a function. Okay. All right, our learning goals. Demonstrate an understanding of functions, representations, and their inverses, and make connections between the algebraic and graphical representations of functions using transformation. So we're not going to spend a lot of time on this in the beginning of chapter 2. We're going to focus more of it on the end. But the first couple sections, this will be our focus right here. So it is to demonstrate an understanding of equivalence, which just means that something is equal as it relates to simplifying polynomial, radical, and rational expressions. So a little bit more emphasis on rational expressions. So rational expressions, they're basically like fractions. So, and we're going to have a polynomial expression on the top. So maybe something like 2x plus 1. And on the bottom, maybe we have a quadratic expression like x squared minus 1. So this is an example of a rational expression because it is in the shape of like a fraction. Okay. Also, we could have something like 1 over square root x minus 1. That's also a rational expression. So our variable doesn't need to be in the top as well. It just needs to be uh, at least in the denominator for it to be considered a rational expression. Okay, so today we're going to focus on equivalent expressions. Okay, so here's kind of a good example of equivalence. So this is just a picture of the Mars Climate Orbiter. And this is a little bit before your time. Sadly, it crashed on its first day of orbit, September 23rd, 1999. This probe was sent out by NASA in order to pick up, I believe it had to do with information regarding like climate and weather. And so what happened was there were two different groups of scientists working on this project, and there's a lot of complex calculations that need to be made. And one group was working in metric system of units, the other group was working in the imperial system of units. So I don't know where the mix-up happened, what it looked like, but it could have been something like as simple as one calculation was made in kilometers and the other group was using miles, and they didn't convert between the two. So um, yeah, you would think with NASA, with all their engineers and nerds on board, that they would have not made a mistake like this, but sometimes these mistakes happen, especially when there are really complex solutions that need to be made or calculations that need to be made. And so, even though they have systems that they always put in place to check these things, sometimes they just get overlooked. So, usually, what engineers try to do is they try to take anything that's complex and simplify it as much as possible. And when you do that, it's then easy to compare different things. So if you don't simplify your expressions that you're working with, then things look really, really messy. So that's what we're going to do today. We're going to take a look at algebraic expressions, and we're just going to learn how to simplify them and see if they are equivalent. Okay, so yeah, let's begin. So how can we determine if algebraic expressions are equivalent? Well, the first way is to just simplify them algebraically. Okay, simplify both expressions to see if they're the same. If you can do that, then you prove that they are the same no matter what. So there's some other methods that don't prove, they only suggest that algebraic expressions are equivalent. So that would be something as easy as just checking for several points. So if you have two expressions, you could try to calculate a couple points and see if those points are shared between the two expressions. You could also graph both of them. So if you graph both those expressions on the same axes, if they're equivalent, you should see identical graphs. So you might be wondering, okay, well, how come this method isn't accepted if you graph them and see they're the same? Well, sometimes graphs can look really, really, really similar. And they may be similar actually everywhere except at a couple points or even just one point. So we'll talk about that a little bit later. So number three, you can easily really be deceived if you're just graphing to try to see if two things are equivalent. Okay, here's our first example. So we want to determine whether two functions are equivalent. So we're given this one. a little bit of a complex quadratic, and then we have this quadratic here. So we want to see if these are indeed the same. Okay. So our first approach is we're going to test 3 different values for x. That's what we'll do here. We're going to take those values and we're going to plug them in for x in our expressions, and then calculate, and we're going to see if these are going to be the same. Then what we'll do is we'll check this algebraically. We're going to set this one equal to this one, and we're going to simplify them and see if my left side is equal to my right side. And if we can prove that, then we've definitely proved that these two are equivalent. And then lastly, we'll just go ahead and we'll graph, and we'll see if the graphs look the same. Okay, let's get this one started. So I'm going to substitute -1 into my f of x function. So basically what I'm saying is I'm going to calculate f of -1. Once I'm done calculating that, I'm going to calculate g of -1, and I'm going to see if they're the same. So here it goes, f of -1. We have 2 times -1 minus 1 squared plus 3, whoop, that's in a bracket, 3 times -1 minus 2. Okay, and close that up. So I'm now going to try to figure out what's in here. We got -1 minus 1, that's -2. And then now we'll figure out what's in here. So 3 times -1 is -3. So -3 minus 2 is -5. So I got -5 in that next bracket. Okay, this is going to work out to -2 squared is +4. So I'll put that right here. That's +4. So 2 times 4 is 8. And then we got 8 minus 5. That's just 3. So f of -1 is 3. Let's try g of x. Let's plug the -1 in. So we're going to plug it into here and here. 2 times -1 squared minus -1. So -1 squared is just 1. So our first term is just 2. And we have minus -1. Minus a negative means +1. And yeah, we get the same thing. So that's just one value of x. So this could be coincidence that those are the same. That's why we're doing a couple more. Okay, this is still inconclusive to prove they're equivalent, but it's at least a step in the right direction. Okay, now we're plugging in 0. So f of 0, we have 2 times 0 minus 1. This is going to make our calculations really easy. Oops. That 3's got to be in the bracket. 3 times 0 minus 2. So -1 squared is just 1, and 2 times 1 is just 2. So this first part is just 2. 3 times 0 is 0, and I'm left with just -2. 2 minus 2 is 0. Let's try g of x. G of 0 is going to equal 2 times 0 squared, so that's all going to go to 0. Then we got minus 0. Well, that's just a big 0 for that one. So those are the same. And lastly, we'll plug in 1. So f of 1 is going to be 2 times 1 minus 1 squared. That's easy. That's just 0. And then we have 3 times 1 minus 2. Okay, so this is 0 right here, which makes the whole thing 0. And we have 3 minus 2 is 1, so we got 0 plus 1, so this is just 1. And let's try our last one. Let's do g of 1. 2 times 1 squared minus 1. That's going to be just 2 minus 1, which is also 1. So far this really checks out. These are the same for f of x and g of x. We can see there's some equivalency so far. However, we just don't know if it's a fluke. So if we want to prove they're the same, let's algebraically, we're going to set them equal. That's what we got set up right here. Okay, we want to see if they are equal. So I'm just going to kind of rewrite this out here because I don't like the f of x and g of x in there. So we're going to make it look like more of like an equation. Now, this plus with the bracket, this plus brackets here, whenever you're adding brackets, you can just drop them, right? we can do 3x minus 2. Okay, it looks a little bit cleaner. And this is all equal to my 2x squared minus x. So we're going to have to take care of this guy right here. This binomial squared, we're going to have to do some FOIL for that. So this will be 2 times x minus 1 times x minus 1. Then we have plus 3x minus 2, and this is equal to 2x squared minus x. So I'm not going to take any of this and bring it over to this side. I'm trying to show that these are the same. So I'm basically just working with this left side, and I want to simplify this as much as possible all the way down, and hopefully my last line I could say that yes, this is the same as this. So let's do some FOIL here for these. We're going to distribute in like that. And we have x times x is x squared minus x plus 1. Close that up. And then we have plus 3x minus 2 equals our 2x squared minus x. Now we're going to distribute that 2 in to each term. Okay, I'm just kind of drawing it that way. I know we're going to collect like terms for that. So this is just going to end up looking like 2x squared minus, well, I guess we'll collect it in the next line. We'll do minus 2x, oops, got the x there, plus 2. And we have plus 3x, whoops, 3x minus 2. So we should see a lot of things collect and to give us just 2 terms. So I have an x squared term here, 2x squared. So that's going to stay. There's no other ones. The rest are all x terms here. So I got negative 2x minus 2x plus 3x. So that's minus 4x. And then we have plus 3x. That's just going to be minus x. So I have minus x here, and I'm going to cross these guys out because I just used them. And then we got 2 minus 2. Well, that's just 0. So there we have it. We can see that these are equivalent expressions. So we can say, yes, therefore, g of x equals f of x. Okay, that means they are equivalent. Okay, and they're equivalent everywhere. You can put any number you want in for f of x, and if you plug it into g of x, you're going to get the same thing out. Let's see how this looks graphically. So I actually have some ordered pairs here because when x is negative 1, I got my y value. So I'm going to go ahead, I'm going to plug those. So we got negative 1, 3. That'll be about right here. There's 3, there's negative 1. And we got when x is 0, y is 0. So we got that point. And then my last one, when x is 1, y is 1. So that'll be about right here. We know that both of these are quadratics. They both open up. So we can easily see that these are going to go through. They're going to go through something kind of like, probably like that here. So the vertex isn't here. I know you might want to draw it like that, but it's not quite like that. So, all right, let's. So this actually is both of these. This is f of x and g of x. Okay. Now it's kind of really hard to tell just from us drawing this, but if we go into Desmos, we could really see for ourselves here. So I'm going to plug in the first one. I don't really need these brackets, but I'm putting them in anyway. Okay, that's the first one, and then the second one. All right, so you notice I have both of them graphed. You can only see the red curve, but if I turn it off, you can see the black one is right behind it. They're right on top of each other. And if I zoom into this a bit more, you can see what I meant, how the vertex wasn't at the origin. So yeah, those are completely identical. So Looking at the graphs is a good way of seeing if they're equivalent, but it's not like completely conclusive. So for these parabolas, it works really well, but you're going to see for some other graphs, sometimes they might look like they're 100% the same, but there could be just one little point that's off. And we're going to see that in our next example. So thanks for tuning into this video, and I will see you in the next one where we look at our next example here.